In the previous video, I went over these basic properties of logarithms listed here. Some of these carried over to the common logarithm of base 10, which is simply written as log of a, where we assume that to mean log base 10 of a. One of the properties was the power rule of logarithms, where we could rewrite log base a of b to the n as n times log base a of b. A special case of the power rule is the reciprocal rule, where the exponent n equals -1. The reciprocal rule is log base a of 1 over b equals negative log base a of b. This is derived using the power rule, and I'll show you how. So let's say we have log base a of 1 over b. This is equivalent to log base a of b to the -1, because 1 over b is equal to b to the -1 by the negative exponent rule. And we can use the power rule, which is log base a of b to the n equals n times log base a of b, to rewrite this as negative log base a of b by bringing the exponent of -1 to the front of the logarithm as a constant multiple. And of course, -1 times log base a of b is just negative log base a of b. So log base a of 1 over b is equal to negative log base a of b. So let's do some examples showing how we could use the reciprocal rule of logarithms. So let's say we have log base 2 of 1 over 4. This is equivalent to negative log base 2 of 4, since in this case, 1 over b is 1 over 4, so when we add a negative sign at the front of the logarithm, the argument becomes 4 instead of 1 over 4. The argument is the top part of the logarithm, so in log base 2 of 4, the base is 2 and the argument is 4. In general, an easy way to remember how this rule works is that if we add a negative sign to the front of the logarithm, we need to take the reciprocal of the argument. And of course, the reciprocal of a number just means dividing 1 by that number, which means the reciprocal of any non-zero real number, a, is 1 over a. So here's another example. Log base 2 of 7 is equivalent to negative log base 2 of 1 over 7, because the reciprocal of 7 is 1 over 7, and we add the negative sign at the front of the logarithm. So here's another one. Negative log base 2 of 5 is equal to log base 2 of 1 over 5. Since if we take log base 2 of 5 and apply the reciprocal rule, we need to take the reciprocal of the argument 5, which becomes 1 over 5, and add a negative sign at the front of the logarithm. But since there was already a negative sign before the logarithm, the two negatives cancel out, and we just end up with log base 2 of 1 over 5. So here's another example where we could use the reciprocal rule of logarithms. Let's say we have log base 2 of 49 plus log base 2 of 1 over 7, and all of this is divided by log base 2 of 49 minus log base 2 of 1 over 7. We don't know the exact values for each of these individual terms, but if we apply the properties of logarithms, we might be able to simplify this into an exact expression. 49 is equal to 7 squared, so we can rewrite log base 2 of 49 as log base 2 of 7 squared, and we can use the reciprocal rule to rewrite log base 2 of 1 over 7 as minus log base 2 of 7, since the reciprocal of 1 over 7 is 7, and we just need to add the negative sign at the front of the logarithm. And all of this is divided by log base 2 of 7 squared, which comes from the log base 2 of 49 in the denominator, and minus log base 2 of 1 over 7 is the same as plus log base 2 of 7, since we take the reciprocal of the argument 1 over 7 and we flip the sign, so the negative in front of the logarithm becomes a positive. If we apply the power rule of logarithms, log base 2 of 7 squared is equal to 2 times log base 2 of 7. The minus log base 2 of 7 in the numerator stays the same, and all of this is divided by 2 times log base 2 of 7, which comes from the log base 2 of 7 squared term in the denominator, and the plus log base 2 of 7 stays the same. So if we combine like terms and simplify, this becomes log base 2 of 7 over 3 times log base 2 of 7. And the log base 2 of 7 in the numerator cancels out with the log base 2 of 7 in the denominator, so this is just equal to 1 over 3. So the reciprocal rule of logarithms also applies for the common logarithm of base 10. So log of 1 over b is equal to negative log of b. And recall that log of 1 over b is the same as log base 10 of 1 over b, and log of b is just log base 10 of b, because the common logarithm is the logarithm of base 10. So if we have log of 1 over 100, this is just equal to negative log of 100 using the reciprocal rule for common logarithms, since we take the reciprocal of the argument 1 over 100, which is just 100, and then we add the negative sign at the front of the logarithm. This is basically the same rule as the reciprocal rule for logarithms, except applied to the special case of the common logarithm, where the base is 10. If we have log of 5, that's just equal to negative log of 1 over 5, since we take the reciprocal of 5, which is 1 over 5, and we add the negative sign to the front of the logarithm. If we have negative log of 1 over 2, that's just equal to log of 2, because we take the reciprocal of the argument 1 over 2, which just turns out to be 2, and then we invert the sign. So we had a negative sign at the front of the logarithm, so it just becomes positive, and we end up with positive log of 2. So here's an example for using the reciprocal rule for the common logarithm. We can rewrite log of 25 in the numerator of the expression as log of 5 squared, and the plus log of 1 over 5 is the same as negative log of 5 using the reciprocal rule. And log of 125 in the denominator is equivalent to log of 5 cubed, and minus log of 1 over 5 in the denominator is the same as plus log of 5 using the reciprocal rule. We can rewrite the log of 5 squared in the numerator as 2 log of 5 using the power rule, and the minus log of 5 stays the same. In the denominator, log of 5 cubed is equivalent to 3 log of 5, and the plus log of 5 stays the same. We can combine like terms and simplify this as log of 5 over 4 log of 5. The log of 5 in the numerator and the log of 5 in the denominator cancels out, and this just simplifies to 1 over 4.